So this is the cool thing about angular momentum, right? L is I omega, right? Is that it's conserved, okay? And there's two ways that it's conserved. Here I'm talking about the conservation of the magnitude of angular momentum, but the direction of it is conserved. So if you have a spinning gyroscope, okay, it's going to tend to preserve the direction that that axis is pointed. And this is why gyroscopes are hard to like point in a different direction, maybe once they're spinning fast, right? So the direction is conserved and also the magnitude, okay? And if you look at the magnitude here, the concept is that if we have a large moment of inertia and a small angular velocity, if we somehow reduce our moment of inertia, the angular velocity has to increase. And every Tualatin student understands this. There's those gates at Ibach Park, right, where you pull yourself in and makes you spin super, super fast. Okay. Here's a video that kind of shows you this. Here, let's just play it. All right. So notice this is angular momentum. So she's got her leg out. Her moment of inertia is big in this picture, right? Once she pulls that leg in, though, watch, she's reducing her moment of inertia. And so if I get small, the angular velocity gets really big. Okay, so this is how ice skaters can change their angular velocity, right, without any external torque. It's basically they're isolated. It's on a frictionless surface like that. Okay, so when you pull your arms in, you tend to spin faster. Or gymnasts, when they tuck as they're doing a flip, they tend to rotate quickly, and then they can come out of the tuck and rotate more slowly. Okay, and I've got lots of demonstrations, so I'll show those to you in class. Let's take a look at the concept of why do you speed up. Okay, imagine if you've got a wheel that's spinning like this. Okay, there's point B and there's point A. Okay, since the velocity, your tangential velocity is omega r, the farther out you are, the faster your angular velocity. If you're twice as far from the center, you're going to be going twice as fast, okay? If I bring B, if there's a mass out here and I bring it into A, say like I move my arms in, okay? Notice that I'm moving B to a place where the velocity is slower. So I have to slow B down, don't I? B has got more energy or something like that, right? Okay? And so to bring B into there is to slow it down. Well, to slow it down would be to push on it this way, right? So you take that mass, if you bring it in, it's going to tend to go this way, so you have to push it back that way. Well, for every action, there's an equal and opposite reaction. So if I'm pushing that mass this way, the mass is pushing us this way, which is, of course, a torque, which would speed us up. Okay? Yeah, that's kind of cool, right? But anyway, that's why it is conserved. You can look, I've got some examples here of the calculation. The calculation is pretty basic.